I think that works. I'm George Anderson, the president of the NCOSE Chesapeake chapter, and I want to welcome everybody here tonight. I'm especially pleased to announce our speaker, Dr. Slavinsky. He's going to give us, I think, a very in-depth treatment on this subject that a lot of us have been hearing a lot about, and a lot of hobbyists and a lot of YouTube people have made it seem like something that not only is a manufacturing technique, but an exciting hobby. So hopefully we're going to learn enough to know what the difference is between the hobby and the industrial applications. So one other thing before I pass the microphone, and that is we have some handouts at the rear for a number of different organizations. One is the master's program at the University of Maryland, and there's another that hasn't arrived yet, or I'd tell you about it, it slipped my mind, but it's equally important. So check that, if you will, as you leave. So without further ado, here's the microphone.
I've got one. Thank you. Yep. Great. Thank you. Can everybody hear me okay? So thank you for the kind invitation to come and speak to you tonight. I'm actually a veteran of the Johns Hopkins University Applied Physics Lab. I've been here for 8 months. Previously spent 25 years working for the federal government at the National Institute of Standards and Technology. And I'm thrilled to be able to be involved in this area of additive manufacturing, and also to share with you some thoughts tonight on the hype and realities of additive manufacturing. So before we get started, I want you to imagine a world where you and your family members and your neighbors and pretty much everyone you know has a device. And let's say this device is about the size of a microwave. And imagine that you can use this device to make pretty much anything, any type of trinket or gadget or tool. And you can use a variety of materials. You can use plastic, you can use metal, you can do food, you can do electronics, you can do cells, okay, biological structures. What would you do with such a machine? What would the world look like with such a machine? Would it look something like this? I don't know if you guys, hopefully you guys know what this is, but this is Star Trek, Captain Jean-Luc Picard on the Enterprise, tea Earl Grey hot, and his replicator makes him instantly a cup of tea. And this device, this replicator device, has some prominence in the Star Trek world. And I think it's also interesting that Gene Roddenberry, the creator of Star Trek, also paints a very positive picture of what Earth is like in the 23rd or 24th, where there's no poverty. That are called additive manufacturing devices. So it's remarkable, the vision of additive manufacturing, the things that people talk about when they talk about additive manufacturing are very imaginative. So these are things that I've heard, perhaps you've heard similar things as well. You know, we're going to print hearts, we're going to print livers, you know, an organ goes bad, no problem, we'll just make a new one for you. Or we're going to do complex metal components for jet engines. Or we're going to be able to print parts on demand for legacy military systems. The B-52 bomber, when it's finally taken out of service, will have a service life of 90 years. Okay, it's not easy to find parts for something like this. And even if you do find a part, you have to transport it and protect it and get it to the front line. Wouldn't it be much better if we could just make metal parts on demand? Or maybe we can do cars, or maybe we can put devices on deep space missions, okay? Because you know, if you're an astronaut on a deep space mission and something goes wrong, you can't pull over to the side of the road and fix it, right? But you also don't have space okay, on board to have an infinite supply of all the possible parts you might need? Wouldn't it be great if you could just print parts on demand? And of course, my favorite is robots, right? So people have talked about it. We're going to print robots. We're going to be able to print the exoskeleton and the circuitry and the outer skin and the software all at once, all right? All at once, all in the same machine. And when we're done, the robot's going to knock on the door and say, "Let me out," right? I mean, this is the vision. This is what people talk about when they say additive manufacturing. And you don't have to look very far either to see that this area gets significant media visibility. This is actually a pretty old slide now. This is a couple of years old, but these were some of the things that were in the press, the popular press, and some of the trade journals, 3 and 4 years ago. But you can look in the paper or on the net pretty much every day and see something new about additive manufacturing. It's getting significant visibility. And people are saying some pretty remarkable things. Complexity is free, right? Doesn't matter how complex your part is. We can make it, no problem. One day we're going to print an engine, metal engine, no problem. We'll do it right here in the garage, right? We're going to go right from art to part. One of my favorites. I'll tell you later why I love that one so much. Or additive is the third industrial revolution. Well, what does that even mean? Okay. So these are the types of things, and you've probably heard statements like this or similar statements or other statements about that. There's a lot of hype about additive manufacturing. My favorite quote when it comes to additive manufacturing is this one from Jeremy Su, who had this in an article in Tech News Daily a few years ago, where he says, "The technology could end up affecting every major industry and have an even bigger impact on US manufacturing than the robot revolution." So think about that for a minute. Not just select industries, every single industry. And so if you were to think about it for a few minutes and come up with a list of those technologies in the past 200 or 300 years that have affected every single industry, you'd have a very short list. Electricity, the personal computer, the internet, okay, those types of things. How many things would be on that list? 5, 6 maybe, okay? Additive manufacturing has the potential to be listed with those other technologies. And along with all the hype and the growing hype, we see a rapidly growing additive manufacturing industry. So if you look back a few years ago, in 2011, there were 1,600 articles published on additive manufacturing or 3D printing, okay? A year later, there were 10 times that. I don't have statistics on the last couple of years, but a 10-fold increase in just 1 year. For those of you who are familiar with Kickstarter, this is one of those crowd-funded projects. 3 of the top 10 Kickstarter projects are 3D printers. The total additive market in 2009 was $1 billion. And 2 years ago, it was 3.1 billion. Now, a couple weeks ago, I had to update this slide, and I sort of chuckled when I looked at the predicted worldwide sales of products and services. So just 2 years ago, when I originally had this slide, they predicted that in 2016, it would be a $3 billion market. Well, we've already surpassed that. Okay, the new figure for 2016 is 7 billion. And for 2020, just a few years ago, they were predicting 5 billion, and now they're predicting $21 billion. So the market is growing very rapidly. It took 20 years for the industry to reach its first billion in size, but only another 5 to reach its second billion. And then if you look at the number of machines that are out there, there are 70,000 industrial machines that have been sold and installed since 1988. And by industrial machines, we mean machines that cost more than $5,000. And of those 70,000, over 10,000 were just last year. And similarly, if you look at the consumer market, and now these are machines that are less than $5,000, okay, these are the types of machines that you would buy yourself and have in your garage or your basement. There have been 140,000 consumer machines sold since 2008, but over half of those were last year. So along with the hype, we see a very rapidly growing industry and market. I like to show this as well. I don't know how many of you are familiar with the Gartner hype cycle, where he looks at various technologies and starts with an innovation trigger, a peak, what he calls a peak of inflated expectations, and then the trough of disillusionment, right? It's sort of when you wake up and realize what's going on. And then the slope of enlightenment that finally gets you to some stable plateau of productivity. And he's put on here a few additive manufacturing or 3D printing technologies. 3D bioprinting systems is sort of on the rise right now, which I tend to agree with, although he says it's going to plateau in 5 to 10 years, which might be a little optimistic. And then over here on the enterprise 3D printing, which I think is referring to the more industrial systems, he says that we've already passed through this trough of disillusionment. It's going to be 2 to 5 years, which again, I think is a little bit optimistic. But the interesting one is up here. It's the consumer 3D printing, where we're still very close to the peak, right? We still have a lot of hype, a lot of hopes and dreams for additive manufacturing or for 3D printing. And so the question is, how bad is the crash going to be, okay, when some people are finally able to separate the hype from the reality? And why do I worry about this? Why do I worry about the hype? Because I was around in 2000 when there was another industry, another technology that had a lot of hype, and it was called nanotechnology. And there was a great deal of hype at the time, and there were visions of, we're going to make robot flies, right? These things are going to fly around the room, and everybody will have one. And when you go to the doctor's office, he's going to put a little miniature submarine in your veins, and he's going to do his diagnosis that way. And by the way, we're going to have these things really fast, right? And they haven't materialized yet. And that's not to say they won't materialize. Certainly people are still working on these things. Certainly these things are possibilities, but they haven't happened yet, and it's already 15 years. So we need to be a little bit careful when we talk about the hype of additive manufacturing, that we don't disappoint people the same way that I think some people have been disappointed with nanotechnology. Okay, so now that I've sort of given the hype and all of the hoopla that goes along with that, let's talk about what additive manufacturing is. So traditionally, when you want to make something, you usually use a subtractive process. So in the case of a chess piece, you start with a chunk of something, maybe it's wood, maybe it's metal, and you cut away everything that you don't want. And everything that you cut away is scrap, right? Chips and pieces like that are scrap. The limitation of a process like this is the physical cutting tool. You can't get that tool everywhere. You're limited into where you put that tool. You can't cut out an interior section of that part because you can't get your tool inside of the part. Now, additive manufacturing does the opposite. Instead of cutting away material, we build up material one layer at a time. So now you can imagine if you have a complex part, as long as you can deconvolve it into layers, now you can do things that have holes and cavities and other complex features in there that you wouldn't be able to make using a subtractive process. Now, fortunately, we have actually an industry-accepted definition for what additive manufacturing is. Okay, so additive manufacturing, as defined by ASTM International, a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. And so I hear people all the time talk about, oh, well, it's welding, or it's this other thing. Well, the two important distinguishers are 3D model data drives the process. There's a direct link from a design into the process, and then layer upon layer. So certainly there's lots of other processes out there that are similar to additive manufacturing, but they probably don't have these two things together. Okay, so welding, although welding is similar to additive manufacturing, and there's some phenomena with melting and cooling associated with welding that's similar to additive manufacturing, they really are distinctive things. Now you'll notice that the ASTM in their definition also has a number of synonyms that are published. So you're probably familiar with many of these: additive fabrication, additive processes, additive techniques, layer manufacturing, et cetera, et cetera. But which term is missing from this slide? 3D printing. 3D printing, the wonderful, terrible term. 3D printing is also defined by ASTM International as the fabrication of objects through the deposition of a material using a printhead, nozzle, or another printer technology. So basically, if you have an additive manufacturing technology that has a printhead or a nozzle, if it looks like a printer, if it moves like a printer, if it smells like a printer, it's probably a 3D printer. What gets confusing is that everyone, and by everyone I mean the popular press predominantly, uses 3D printing synonymously with additive manufacturing. It, in general, refers to processes, however, that are low-end in price or overall capability. So why is this a wonderful, terrible term? The term is wonderful because everyone can conceptualize what 3D printing is. I know what 3D is. I have a printer. Add them together, 3D printing. I know what that means. I can conceptualize that. The problem is that when you start using the term 3D printing synonymously with everything, you confuse people's expectations. So you see something in the newspaper that says, we're going to 3D print a metal jet engine. No, you're not. Okay, you're going to use it, you're going to make it perhaps with metal additive manufacturing, but you're certainly not going to 3D print it. So this is something that I get on my soapbox about, apologies, but I hope that you'll help me with this the next time you're at a cocktail party and someone comes up to you and says, hey, have you heard about this great thing, 3D printing? Your proper response is, oh, you mean additive manufacturing. Okay, so help me with my quest to use the right terms here. So to further beat the dead horse on this, I've put together, I think, what it helps clarify for people the difference between 3D printing and additive manufacturing. And I've done it this way. So if you look at part quality and functionality as a function of three different things, which all happen to scale the same way: system costs, infrastructure requirements for the machine, and level of expertise required, you get a picture that looks like this. So for those systems, those consumer systems that you can buy for your use at home, let's call those 3D printers, okay? The costs are very modest. You don't have really much in the way of infrastructure requirements, right? You can just plug it into your wall outlet, okay? The level of expertise is very low, okay? Anyone can do it, okay? A high school student, a grade level student, okay? Pretty much anyone can run these machines. Now, if you start getting into the more, but the result is that you get parts that are, you sort of get what you pay for, right? The parts are of lower quality and of lower functionality. Now, if you move up into the additive manufacturing polymer sphere, okay, now the systems are more expensive, tens of thousands of dollars, hundreds of thousands of dollars. The infrastructure requirements are a little more significant. Okay, you can't just plug it into the wall. You probably need some high voltage. You might need some ancillary systems, okay, to deal with the lasers in your device or other things for post-processing. And the level of expertise is going to be a little more sophisticated too. So it might be easy to run the machine, okay, perhaps. You know, maybe a college student can do it, all right? But there might also be some other expertise that goes along with that that's needed. And then finally, additive manufacturing of metal, which gives you the highest quality and functionality in terms of parts, are the most expensive systems. Now you're talking about $1 million systems. The infrastructure requirements are severe. It's not only the high voltage, it's being able to use inert atmospheres for your build. It's being able to have subtractive machines nearby, okay, because you need those for post-processing and for build plate reconditioning and other things like that. And the level of expertise, again, it's not necessarily hard to run the machines. If you can, I mean, I can run the machine. If I can run the machine, anyone can run the machine, right? But if you can run a CNC machine, you can probably run one of these machines. But you still need expertise to decide what process parameters to use and what type of post-processing treatments and things like that. So I hope I've convinced you that there is a difference between 3D printing and additive manufacturing. So we're fortunate in that the ASTM also defines for us the 7 different types of processes. So we have definitions for these. They are binder jetting, directed energy deposition, material extrusion. Here's where we get a little more confusion, because a lot of people refer to vendor trademark machines as processes, okay, and they're not really processes, okay? So the fused deposition modeling, that's by one company's process. It's actually a material extrusion process. We have material jetting, powder bed fusion, and again, some synonyms or things that are like synonyms that people use to associate with particular machines: sheet lamination and vat photopolymerization. So, sorry, I have a slide for each of these. I'm going to go through them very quickly, okay? The key point for all of these processes is just to keep in mind that it's data-driven, okay? Remember, we have some CAD or some digital design that drives our process, and we're doing things layer by layer. Everything else is just detail, okay? So the binder jetting process is one in which you have a bed of powder, and this is a part being built, so we're in the middle of the build, and you have some type of windshield wiper or roller, and you spread a layer of powder over your part, and then you use a 3D printer type head to deposit binder or glue. Okay, so for each layer, you're gluing together your particles. And then what you end up with when you're done is you end up with a very fragile green part. Okay, and you can do this for polymer, you can do it for metal, you can do it for a variety of materials, but you end up with a very green part, and you usually have to do some significant post-processing to get a part that won't fall apart in your hands. Directed energy deposition, this is generally associated with metal, okay, with metal powder. So in this case, we have an energy source, okay, from above. So we're looking at things from the side here. Here's our part, and here's our molten metal. So we've got an energy source. It could be a laser, it could be electron beam, and we're feeding either wire or we're blowing powder into this heat zone, okay, and then we're moving this, okay? So we're actually depositing material and melting it on the fly, okay? So that's how directed energy deposition systems work. They work pretty well. They're good for repair. If you have an existing part that you want to, that maybe has some cracks or you want to put a new surface on, it works great for that. The feature resolution is not so good with a system like this. Then we have material extrusion. So this is what the maker bots of the world do, as well as some of the more expensive industrial systems. In this case, you have something that looks and smells and tastes like a print head, okay, and you go back and forth and you deposit some molten polymer, typically molten polymer, to build up your part layer by layer. This is a very popular process in additive manufacturing. Material jetting is very similar, except you're just depositing stuff. You're just squeezing stuff through the tube, okay, like a tube of toothpaste, and it's generally a photopolymer or wax. Powder bed fusion, this is my favorite. This is the one that I'm most involved with. This is the process that gives you parts of the highest quality and highest dimensional control. It's similar to the binder jet process, where we have a powder bed over here and a reservoir of powder, and we scrape the powder across the part, and then we use a laser to just melt that portion of the powder that corresponds to that layer of the part. Okay, so this is a very nice, very good process. Sheet lamination, don't know very much about this. This is not a very popular process. In this case, you're using energy to basically get sheets of material to stick together. Okay, and then you're using a laser or something else to cut out the proper shape for each layer. And then finally, vat photopolymerization. This is a process in which you're depositing a fluid, a liquid, which is a photopolymer, and then you activate it through light, either infrared or some other wavelength of light, to solidify that liquid. So those are the 7 processes very quickly. But why do we care about these? Why is this so great? Well, as I mentioned, you know, we're able to realize complex structures, okay, with this. We can make complex geometries. We can make parts that have internal features. It's a highly customizable process. So if you have a base part and you want to customize it, say it's a medical part, and you want to customize it for a variety of people who have different sizes and shapes, it's very easy to do that. The overall production time is very short compared to traditional processes. We don't have to worry about tooling or customized fixtures or path planning. So this is really important if you have design changes. So you can imagine traditionally, if you have a design and somebody wants it made subtractively, you have to come up with your tooling and your fixtures and how you're going to orient it and hold it, and then you have to plan how you're going to cut away the material. And then when you're done, you take that to the designer, and the designer says, yeah, that's good, but it's not quite right. So here's a new design. So you have to scrap your tooling and scrap your fixtures, okay, and redo your path planning. And if you do that enough times for a given part, you get really frustrated, and it takes a real long time. Okay, but with additive, because we can go almost directly from our digital design to our part, we don't have to worry about tooling. We don't have tooling. We don't have fixtures or things like that. So it's very fast and easy to make design changes. We can produce multiple parts in one build. There's an example of that up here, okay, where we have a build plate from a machine. You can see it's not just one type of part. It's a variety of parts that are all being made at once. So you're really only limited by your build volume. We can do small lot sizes. We can even do, you know, lot sizes of 1, okay? We can do all-in-one assemblies. I'm going to talk about this part a little bit later. This is a part that's been getting a lot of attention lately. This is the GE aircraft fuel nozzle for their next-gen LEAP engine. Traditionally, this part was made out of 20 different parts, and then it was assembled through a welding operation. But you can imagine if you're doing a welding operation of 20 different parts, there's a good chance for error, right? And the parts get scrapped. Here, they're able to incorporate all those parts into one, and it's all built in one operation. We can do biocompatible materials. So on the metal side, we can do cobalt, chrome, and titanium. We can also do bioabsorbable materials. So on the polymer side, we can do PLA. So if there's some implant that you don't want to remove, okay, it can actually dissolve and be absorbed by the body. We can engineer porosity. This is particularly good for implants like this joint here, okay, where there's a porous structure on the surface that allows for good tissue integration, okay, into that part, which is something that you want. Additive works well on hard-to-machine materials, so things like titanium, which if you were to do traditionally, you would have a lot of tool wear. Okay, we can do that pretty easily. And then we can also do topological optimization. So we can do this bracket here, which is an Airbus design. This is the traditional part back here. And then you can optimize that part to remove a lot of the material and get rid of a lot of the mass, but still keep the strength and the stiffness. Okay, so another advantage. So those are all the advantages of additive manufacturing. Now I need to go through this quickly since we're talking about hype and reality, right? Some of these things that people are saying about additive manufacturing. Complexity is free. We can produce anything, right? Well, complexity is not free. It's certainly inexpensive. We can't make everything additively, but we can make many things, okay? Art to part, which means there's a direct path from your CAD design to your part. Almost, not quite. We usually have to do some intermediate steps. So we need to slice that part into layers, or we need to add support structures that we're going to need during the build or things like that. So it's not quite art to part, it's almost. Additive manufacturing is fast. Well, I think as I described earlier, since we don't have to worry about tooling and fixtures and path planning, the entire design cycle, you know, or the entire production cycle from concept to part is relatively fast. The unit process is actually pretty slow. Okay, when we're using additive manufacturing machines, it usually takes, you know, a fraction of a day or several days to make a part. Okay, so the process itself is slow. The overall production cycle is pretty fast. Additive is a push-button technology. Certainly, once you've got a job set up, if you know what you're doing in terms of selecting your parameters and your post-processing, it's not too hard to run the machine. But there's a lot more than just pushing the button on the machine. Some people say that additive is greener than conventional manufacturing, and my answer to that is maybe. We don't have a lot of data on this. It also depends on how much of the manufacturing cycle you include in that calculation. You know, do you start with the production of the material that you're going to feed into the machine, or do you start with the unit process? So we need more information on that. People say that the systems and materials are inexpensive. Certainly the 3D printer class of materials and systems are inexpensive, but the industrial grade systems and materials are not expensive, or not inexpensive. They are expensive. And then additive will replace conventional manufacturing. I love this one because I heard this in my building just the other day where, you know, we've got two sides of the building, you know, people that do additive and people that do subtractive. And one of the, let's say, more experienced guys in the subtractive side was grumbling out in the hallway to one of his colleagues. And he says, this, you know, newfangled additive manufacturing, it's going to replace all of these subtractive machines. You know, then what are we going to do? We're not going to have jobs. You know, well, no, just not quite. Okay. You remember, additive can't do everything. Okay. But also they're complementary. I mean, additive technologies need the subtractive technologies to help with finishing machining and build plate conditioning and other things. So at least in my lifetime, additive technologies are not going to replace conventional manufacturing. Just quickly, since you know, we're talking about it, this compares some of the aspects of traditional manufacturing, so just traditional subtractive manufacturing with additive manufacturing. So you can see that the rate in which we do things, okay, the rate of removal, okay, is much faster on a traditional machine than it is on an additive machine. The volumes are much different, okay, several thousand times bigger volumes on a traditional machine. The surface finish out of the machine is smoother, okay, on a traditional machine. The dimensional accuracy, okay, for a CNC type machine, you probably have dimensional accuracies of about 5 micrometers. On some additive machines, we have day-to-day variabilities of 30 micrometers. Okay, so we're not quite as precise. Path planning, it's really about the same. You can get third-party software to help with your path planning. On the additive machines, that's just part of the machine. It happens automatically. Fixtures and tooling is required for traditional machines, not required for additive. The material costs are very different. So if you're talking about stainless steel, you can probably buy that conventionally for about $5 a kilogram. But whatever you cut away is wasted. Okay, you can't recover those chips and use those chips again. On the additive side, we can buy stainless steel powder for about $140 per kilogram. But whatever we don't use, we can recycle and use again. Okay, so there's very little waste in an additive process. Mechanical properties we'll talk about in a second. Basically, they're comparable with some caveats. And we already talked about design changes and some of these other challenges. You could have excessive tool wear with traditional processes. In additive processes, we have fun with things like thermal stress and process variability and overhangs. Okay, so another key point is just because you can make something additively doesn't mean you necessarily should make something additively. So here are some examples. So if you're just interested in a metal plate that has some holes in it like this, you're probably not going to do that part additively. Okay, it would take a long time. There's nothing complex about this part. Okay, similarly, if you're mass producing something like screw threads, okay, and you're making them in vast quantities, Okay, there's nothing particular about this part that lends itself for additive. Certainly, mass production is difficult with additive. But things that have complex structures, okay, things that have internal structures or that are assemblies of other parts, things that are customized, highly customized, okay, such as these bioimplants. What about this part? What about these little army guys? Well, you probably wouldn't print those additively, but you could make the tooling for that. Okay, so you could make a mold for that additively that you would use for your injection molding. So it's a complex part, right? It's got a lot of features. Okay, you can make the mold for that additively and then let another process use that. What about guns? This is always my favorite. Certainly you could make a gun additively. People have made guns additively. Additive manufacturing is a stupid way to make a gun though, okay? Because it takes too long and it's too expensive, okay? It's easier to buy a gun on the street, okay, than it is to do one additively. People have demonstrated this, you can do this, okay, but it's not a very good use of additive manufacturing. Now, why, so, okay, so we've pontificated about how great additive manufacturing is, right? So why isn't these visions, okay, these great visions and dreams that people have, why aren't we seeing those yet today? Okay, well, there's a number of technical challenges, and now we're focusing mostly on metal, because that's what I do. All the cool kids do metal additive manufacturing, okay? So there are a number of challenges and needs that are associated with metal additive manufacturing. Related to materials properties, related to understanding the process. It turns out we don't really understand the process very well, okay, because it's very difficult to measure the process. This is something that happens very fast with temperatures that are changing by 10,000s of degrees per second or more, okay, over a very small area. So it's a very difficult process to measure. We don't have we have some standards. We don't have very many standards. We don't know how to qualify and certify these parts easily. Okay, which is why you don't see many examples on planes yet. And as we talked earlier, part accuracy and surface finish and speeds and things like that are also all challenges. I want to show you an example of thermal stress. This is a real part. I think I built this part, I'm sorry to say, but this is a test artifact that we built while I was at the National Institute of Standards and Technologies, just to show you that residual stresses in these parts are real and they can be significant. So we have a build plate here and we've fused our part. Our part is fused to this build plate, and this is after the part has been done. And you have these support structures in here that help hold the, actually I think I have a, so support structures are things like this. They're aspects that you add to your part to hold your part to the build plate, okay, especially in the case where you have overhangs or things that might sag during a build. But in this case, we did not make the support strong enough, and the residual stress in the part was too great, and it bent up a corner. This is a metal part, by the way. The most extreme case I've seen is when we made some huge cobalt, and different materials stress differently. Some aren't so bad, some are pretty bad. Cobalt chrome is really bad. So we were doing big chunks of cobalt chrome, and we had it fused to this build plate. This build plate is, you know, it's stainless, it's 1045 steel, it's an inch thick. It's about 10 inches by 10 inches, weighs about 25 pounds. It's a pretty significant chunk of metal, and it's screwed into the machine, and you build your part. My colleague calls me up in my office, and he says, I can't unscrew the build plate. I said, what do you mean? He says, I can't get it loosened. I said, did you eat breakfast? You know, are you sure you can do that? He said, I can't get it loose. So I have to go all the way across campus, you know, to the lab to get, and I get there with the screwdriver and you know, so we get a little wrench. We get a much bigger wrench. It's not budging. Okay, so we popped the heads off of the screws and took out this, remember, 10 inches by 10 inches, 1 inch thick steel build plate, and put it on the table, and we held down one corner, and the other corner was up by 5 millimeters. Okay, that's how much residual stress was in this plate. We ruined the build plate. We called up the vendor. We said, hey, look, this happened. He goes, yeah, it happens sometimes. You know, so the stresses can be significant. People always ask, well, what about material properties? You know, you got your newfangled additive manufacturing, right? Well, how do the material properties compare to a casting or a forging? So here's some data that we took while I was at NIST. And what we did is we built a series of tensile bars. Okay, this is a standard thing for engineers to do. And we built them horizontally along the build plate, and we also built them vertically. Okay, so of course you would expect intuitively that the bars that are built horizontally that you pull this way are going to be stronger than the ones that are built vertically. And that actually is the case. So the horizontal bars with no heat treatment afterwards compared to the vertical bars, and you can see the tensile strength differs by about 10%. But we reserved half of the samples and we did a heat treat on those to try to improve the mechanical properties. And then you can see not only did the mechanical properties improve, but this difference actually became much smaller, okay? And then if you look at the horizontal heat treated specimens and compare it to a traditional casting or forging, you'll see that the properties are the same or even better. And this is something that's repeated over and over again in the literature, okay? It's not just us with stainless steel, but it's people have done this for other materials and seen similar trends. So the answer to the question is, if you do your orientation properly and you do your heat treatment properly, then you can get properties that are very similar to a casting or a forging. I talked a little bit about variability, right, in additive manufacturing. So here's a case where we did a study also at NIST a number of years ago, where we had a group of, we had several groups that all had the same machine, same model, same process parameters. We provided everybody with the same powder and the same design file and asked them to build tensile bars. So to the degree that we could control it, everything was the same. And they sent the tensile bars back to us, and we did the post-processing and we did the testing. And then if you focus up here on these systems here, you'll see that there's quite a bit of variability between the 6 different labs that had the same systems, okay, and kept everything the same. And you can further see this if you look at some of the mechanical properties, so ultimate tensile strength, focus just on the blue, okay, because those are the systems that are the same. Okay, you can see ultimate tensile strength looks about the same, but then the yield strength is sort of all over the place, and now elongation is all over the place, and Young's modulus has quite a bit of variability too. So we don't really understand this system. Okay, there is still some variability. This is one reason why it's difficult to qualify metal additive parts for aerospace. Okay, we thought we did everything the same. Certainly, we controlled everything that was within our control to be the same, but we had some variability. Okay, so what's the future? So we've talked about the hype. Right, we've talked about the vision. What's the future? Well, the good thing about the future is that anyone know who this is? There's Niels Bohr, right, who knows something about predicting the future, right, when it comes to quantum mechanics. Okay, prediction is very difficult, especially when you're dealing with the future. Okay, so how are we going to predict the future? Well, what we can do is we can look at some impressive examples of additive manufacturing today, and then from that, perhaps you can make some educated guesses about what might or might not be possible in the future. So let's just go through and look at a number of areas quickly. So consumer goods. So a lot of attention is being done on the consumer market. So this is the lower quality machines, or maybe the mid-level polymer machines. People are doing some pretty neat things. Nike had a new shoe design for their sprinters that was made additively. This design actually helped them stay in a low position for longer coming out of the starting blocks, which shaved time off of their races, okay? People have done jewelry, camera cases. People have done or tried to do cars, okay, polymer cars additively. A dress that was highly custom. Talk about customized, okay? It would only fit this person, okay? It's made of 60 or so different pieces, okay, polymer that all fit together. It's not gonna fit anyone else, okay? I apologize, a race car is not really a consumer good, but I didn't have another slide to put this on. So people are using metal additive manufacturing for a highly complex and customized engine components in NASCAR or in Indy type cars. So on the consumer goods, you can see there's lots of different examples of relatively simple, inexpensive things that are being done. Everyone here watches Big Bang Theory, right? No? Oh my God. Do some of you watch Big Bang Theory? Okay, so thank you. So if you're a scientist or engineer, I think you have to watch Big Bang Theory, right? So actually this episode was showed yesterday on a rerun. But for those of you who know this episode, this is the Wolowitz Zero Gravity Waste Disposal System, or as Raj would say, it's a space toilet. But in this episode, which is one of the funnier episodes, Wolowitz realizes that his space toilet design, which is up on the International Space Station, has a flaw, and they're going to have a problem, okay? And if you're on the International Space Station, you don't want to have a problem with the space toilet, right? Well, guess what? On the International Space Station, they had a problem with the space toilet not too long ago, okay? And so, you know, up on the International Space Station, they don't have a lot of room for inventory. They don't have a lot of room for parts, right? So you don't necessarily have a new part, okay, that you can just pull off the shelf and stick in the toilet to fix it. So what do? Well, you have to wait for the next supply mission to come, and maybe you have to jury rig a solution. But wouldn't it be great if there was a 3D printer up on the International Space Station? Well, as a matter of fact, NASA last October put a 3D printer on the International Space Station. Now, this is a very modest system. It has a very small build volume. It could build parts about the size of a deck of cards or so. But They're using it, they're testing it. The Europeans got jealous. I mean, also wanted to try this. So they are going to send up their own version of this printer, or perhaps they already have. But you can imagine, but you can imagine in outer space, you know, like we talked about earlier, if you're on a manned deep space mission, you know, you need a part, you know, can't carry them all, can't pull over to the side of the road. It'd be great if you could have this type of capability. I think the next gen Mars rover is slated to have 20 or so different additive parts on it. I teased earlier about this GE aircraft fuel nozzle. This is going into production very shortly. Okay, they've already flown this on a test flight. This is a part that's made that was made traditionally, as I said, out of 20 different components. It's a one-piece design. It has internal features that allow for better mixing of the air with the fuel. It's a more reliable part. It's a lighter part. It has less bad forms of oxides coming out of it. Okay, it's more fuel efficient. So this is a great example of an additive part. Now, of course, GE aircraft engines has spent 10 years and millions of dollars developing this part. But this is a good example of the types of things that we should be able to see in the very near future more routinely. Yes, people are using 3D printers to print food, okay, noodles and chocolates. Not only chocolates, but there are some people who will scan your face and then print it out in chocolate, and then you can eat yourself, I guess. I don't know. So, I mean, this is really happening, right? Chefs are doing this. There's also some people who are using cellular material to print something that looks and feels and tastes like meat, even though it might not really be meat, okay? It might have the same nutritional value, looks and smells and tastes like meat. Now you think, well, would you want to do this? Remember, Gene Roddenberry has this vision for the future of what the Earth would look like. Well, you can imagine if you could develop this technology for places where there isn't a lot of food. Okay, now we're having a real positive impact with something like this. But in the meantime, we'll just, we'll try to stick to the fun things like printing our faces in chocolate. Home fab is taking off. I showed you earlier, 140,000 systems sold in the last 7 years, over half of them sold just last year. It's a booming market. The one issue with this is that not everyone is a designer, right? So lots of people can run these machines, but not many people can design parts for them. Not many people know how to use CAD. But thankfully, there are websites out there where people upload designs for free, and there's thousands and thousands of designs up there. So, and what does the future look like for this? Well, you can imagine maybe in the future something in your house breaks. Maybe a shower curtain rod, or maybe a paper towel holder or something like that, and you really don't want to have to schlep all the way down to Home Depot to get one. You spend 99 cents online, you download a file design, and you print it up in a few minutes. Okay, that's sort of the vision. Models for surgical planning and reference has really taken off in the last couple of years. There have been a lot of really interesting and useful examples where doctors are taking CAT scan data or CT data and printing up models. And this is useful in several different ways. It's useful for surgical planning so that you can get your equipment in order, okay, before it comes into the operating room. And if you do that, then you can reduce the amount of time that your patient is under anesthesia, okay? You can use these models for reference during a procedure, okay, or before a procedure, or in the case of conjoined twins, okay, where the doctors needed to know which blood vessels and other structures were being shared. Okay, that's a very useful thing to do. It's also being used in an empowerment way. Okay, there have been people who have printed up their cancer tumors before and after treatment. Okay, to sort of help them understand what's going on, help them feel like they're part of the recovery, part of the process. There was an interesting case a couple years ago of a gentleman who he was injured over a decade ago. He broke his jaw. And the doctors thought that they had fixed it and they had recovered, but he kept having recurring pain, and he kept going to doctors over and over again, and they couldn't figure out what was wrong. So he was a bit of a tinkerer. He had a 3D printer. He had the CAT scan data, and he printed up a 3D model of his jaw, and he looked at it and rotated it, and he thought he saw something. And he took the 3D model to his doctor and says, "What's this?" And the doctor says, "Oh, that's why you've got the pain." Okay, so you don't really think about this, but we live in a 3D world. We don't always see everything that we need to see in a 2D representation. Okay, but with the 3D models, people are seeing more, and it's really remarkable. I expect to see a lot more of this in the future. Biomedical implants. For people soldiers, veterans who have traumatic brain injuries. There are already examples of both metal and polymer skull implants, okay, to cover up holes in the skull. Some of that work is being done at Walter Reed. Also, as I mentioned earlier, joint replacements. I don't think there's many instances of this yet in humans. There's lots of cases of this in pets, dogs and cats, okay, are getting metal additive joint replacements. In England, not too long ago, there was a elderly woman who had her jaw replaced, okay, with an additively manufactured titanium jaw, okay. This poor fellow, true story, this guy was a construction worker in China. He fell off some scaffolding, landed on his head. You can see the type of injury he had. That injury left him unable to speak. So they designed a customized implant and implanted it in his skull. And the thinking is that his brain will now be able to expand back, okay, to more or less its proper size, and are hoping that his speech will return. So lots of examples of the biomedical implants. There's also lots of hype about tissue, okay, printing biological tissue. So printing cell structures into collagen or printing cell structures into some other structure that maybe you print additively, okay? There are some examples of this sort of at the research level for people to print up bone structures or to print up replacement facial tissues or ears. There's actually a very nice, the ultimate vision, of course, is to do hearts and livers and kidneys and things like that. We're still quite a ways off from that. But people have printed these tissues before, okay, recently. So if we're in the case of liver tissue has been printed, and actually liver tissue that you print, it's not my area of expertise, but my understanding is that that tissue will stay viable much longer than tissue that you take from a biopsy. So what would you do with liver tissue? Well, you can use it for toxicology testing. So if you have medicine, okay, instead of doing a trial, okay, you can test it on the tissue itself and see what the reaction is, okay? And obviously that's a much better situation than doing a human trial. So lots of exciting developments and also opportunities for human tissue. So I thank you for your attention. Let me get to the conclusions. Clearly, the vision for additive manufacturing is very imaginative. We do have some technical challenges that we have to overcome if we want this technology to be more widespread and pervasive. The market, I think I showed you, is growing very quickly. We have some very impressive niche applications reported so far, but be careful when you listen to things, and when they call everything 3D printing. Scrutinize what you hear, okay? When you read these articles, when you hear things in the news, make sure that there's a lot of hoopla out there. So make sure you scrutinize it and understand what they're really presenting, because sometimes they don't get it right, okay, on the reporting side. And I personally have had a drink of the Kool-Aid. Okay, I'm a believer. Additive manufacturing will be a significant disruptive technology. We've already seen that it's slowly becoming that. It certainly will be a very significant disruptive technology in the future. So I thank you for your attention, and I'll be happy to take any questions that you have.
Okay, I have a couple of questions. Yeah, so now you...
I'm sorry, easy questions only.
Yeah, now you print it, so can you test it?
I'm sorry?
Now you have printed it, so can you test it?
So for...
and a couple of questions. What about the materials? And you're talking about volume in, before you print it, what's the ratio, volume to the product? And then, there's biocompatibility issues for human parts and surface structure.
Yep.
So it's not really as simple, I gather, as they hype it.
So how much time do we have? So testing and qualification is a significant issue. We can certainly, and I've showed you some data, we can certainly do lots of material property data on these things. We have a fairly good idea of things like shrinkage and dimensional changes and things like that. But, and the FDA there's already plenty of examples of these materials being implanted into people, okay, either in emergency situations that the FDA has blessed, or there's an FDA process where if you've made a part another way and it's already approved, and now you make it additively and you can demonstrate that it's equivalent, okay, then you can use that part. So we have lots of examples on that. But the qualification issue is a very difficult one, and one that we don't really have time to expand on. I can say that there's a lot of thinking on how to do qualification. We certainly, well, I should say, not everyone can do the GE way. Not everyone has a decade and millions of dollars to do a brute force qualification when it comes to an aerospace part. There are other things you can do that are sort of quickie certifications, and it depends on the comfort level of your sponsors, okay, with those parts. But one thing that we didn't touch on is, maybe I mentioned it, is that on the process side, we don't yet have good physics-based models of these processes. Once we have the physics-based models, in my mind, that's the holy grail on the research side. If we can model these processes and validate those models, then we can greatly accelerate the qualification, okay? Because we can do most of it in a computer. We won't have to do a brute force approach. Why don't we go over here first? Go ahead.
Okay. As with a lot of things where you said that the time it takes to manufacture a component is rather slow now, but usually these things tend to progress. Is there any trend towards the speed with which things have been built that you've seen? That when might it get significantly faster?
So that's a great question. So up to a few years ago, most of the, and again, I'm talking from the metal side because all the cool people play metal. On the metal side, the powder layers were 20 microns, and most machines used a 200-watt laser. Well, now a lot of the systems have double the power on the laser, so 400-watt lasers are even higher, so that they can melt more material at once. So instead of 20-micron laser, 20 microns, that's really thin. That's about half the diameter of a human hair, right? Okay, so now they're getting up to about the diameter of a human hair. Okay, so now they can do about 40 microns or so. So there certainly is a desire to do things faster. The build volume is also an issue. The reason why on many of these systems, laser metal powder systems, the build volume is only 10 inches by 10 inches is because you have a laser and you have a lens system, and you want that laser spot to be consistent across your build. But there's only, when you start getting out to the periphery, there's only so much correction you can do, and things start to distort. So people are talking about doing dual laser systems, 2 heads or things like that to try to speed things up or try to increase the volume. So there is a trend for that. I personally don't see speed necessarily as a significant detractor. Okay, when you consider the entire production cycle, it doesn't bother me too much if things take a day or two. Okay, as long as I know I can get a quality part on the other side. We had a question over here.
Question on electronics, circuit boards. Like one of the interesting things I saw at the JHU Design Day was circuit boards where they were actually using reduction. They were etching out the copper. Mm-hmm. What is the status of actually doing an additive for not only creating circuit boards, but also printing 3D, well, I'm not going to use that word.
That's okay, that's the correct usage.
Okay,
yeah.
3D printing the actual electronic parts.
Sure.
Actually on the board and making them flexible and formable.
Great question. So conceptually what people really want to be able to do is they want to be able to do a base material, let's say a polymer, okay, and then 3D print circuit pathways on top of that, okay, so that you can make some complex parts that maybe have integrated electronics or things like that. Up until recently, the limiting factor has been that deposited electric material, okay, so it's a paste or it's an ink of some kind. The issue has been twofold. The resolution is not really that good, and the conductivity. The conductivity of those materials has been really poor, okay? Now, I say that that's what it used to be because just recently a new company up in New England called Voxel 8 announced that they are selling a new machine that will do exactly what we want it to do, which is it will print a base structure, a 3D part out of polymer, but it will also print a highly conductive ink. And when I say highly conductive, I mean 10,000 times more conductive than all previous efforts to do it, and only about a factor of 10 lower in conductivity than a traditional silver ink or something like that. So we're not quite where we want to be. It remains to be seen if this machine really does what they say it does, because it hasn't been sold yet. It's going to be released later this year. I can tell you that we're in line to get one. Okay, so we're excited about the possibilities and we want to test it out, but we're not quite there yet.
Second to the last question. I'm familiar with overhauling jet engines, and I'm very familiar with, I guess, the powder technology, for repairing parts in the aerospace industry. And the one thing I see missing and I'm curious about is the fatigue comparisons, the ability to withstand fatigue. And of course, in a jet engine, ultimate strength is nothing compared to the ability to withstand long cycle times. Could you comment on that?
So I have not personally seen a lot of fatigue data myself. I haven't, and at NIST we didn't, well, I was at NIST, we did not do any fatigue data, but there are people who have explored fatigue. Obviously, GE Aircraft Engines is comfortable with the fatigue data they have since they're going to install 40,000 of these, fuel nozzles on board shortly. So people have done it. I'm just not that familiar with it.
Presumably they have tested it.
Yes, absolutely, but they also won't share it with you, I'm sure.
Yeah, so what about the variety of materials that you can use to do the printing depending on the application? It's really still in its infancy.
Yep.
And you have to have kind of stores and logistics if you're going, and then what will the nozzles handle for the deposition? And practical issues like clogging in the nozzles and cleaning and so on.
Sure. So in the case of powder bed systems, we don't have a nozzle. We just spread the powder and then melt it. But the point is still a good one. If you look at the commercially available industrial metal machines, and if you look at the materials that the vendors make available, it's a fairly short list. So, vendors will have 8 or 10 or so different materials for each machine. It's not an issue of practicality. If you can powderize it, and if you can have the powder with the right properties, which is another talk, but if you have the powder with the right properties, you should be able to melt it. The difficulty is coming up with the right process parameters. Excuse me. So what laser power, what laser size, how fast can I move my laser? Because the melting, to get the good part, your energy density, okay, how much energy per unit volume you put in has to be correct. If you're short of that, then you don't melt enough, okay, and you don't make a good part. If you're too high, you evaporate your powder, okay? So you have to find that sweet spot. But the way they determine that sweet spot nowadays is empirically. Because we don't have these physics-based models, they have to go through the vendors, okay, they have to go through a lot of trial and error to figure out what is a good process. It might not even be the best process, but what is a good process, okay? So that limits the different types of materials that are available commercially.
So you're really going to have to, you're really going to have to, when you get maturity in the processes, eventually have adaptive machinery or adaptive manufacturing for 3D printing or additive.
Yeah, or a good, or at least a good process model, okay, that gets you most of the way there.
Yeah, I play baseball. So is it possible that I could just print my gear out?
Print your gear out?
Yeah, like my gloves, baseballs, bats, stuff like that.
So so some people are doing stuff with cloth, okay, so that might be possible. I don't know if, I suppose you could probably do a metal bat. It might get a little tricky depending on how thin it is, but certainly I would say probably, some of those components, conceptually, sure, why not?
The same resilience, of the regular?
Quite possibly, yep.
Okay, thank you.
I've never heard anyone ask me a question about baseball and additive, so thank you for that. I'm gonna have to think about that a little bit more. Okay. Well, thank you. Oh, I'm sorry. One last question.
Is there a typical amount of loss due to, things that get vaporized when they shouldn't be, or that get just, lost in the process or stuck in the nozzles, or what's the kind of ratio you're talking about?
Yeah, so
they model that. So
when we do a laser powder bed process, we do have some evaporation. I couldn't tell you exactly what percentage that is, but I can tell you that when we're done with the part and the part is buried in the powder, and you do like an archaeological dig, right, to get your part out, that powder that we recover probably about 98 or 99% of that powder. Okay. The difficulty is if you've got holes and channels and things, especially when it's still on a 25-pound build plate, it's not easy to just tip it over. So you usually use a special vacuum, to get rid of those. But I would say of the powder that remains after the process, you probably get about 98 or 99% of it back. There's some powder that sees a little bit of heat that sticks together that you sift out. Okay, but the rest of it is good to go. Yes, in the back.
Can you comment on NASA work in 3D printing NASA challenges?
So there have been examples, not by NASA, but Lockheed Martin has put a few additive metal parts on at least one of their probes. As I mentioned, NASA is interested in the technology from a part production point of view in outer space. NASA has interest in using 3D printing technologies and native material, either on the moon or on Mars, to print buildings. Okay, so you can imagine a very big additive manufacturing system, a gantry type system where you just pour in, local material and build a heat shield, or you build a dwelling or something like that. Because if you're going to Mars, you can't take a building with you, right? Not easily. NASA is interested in metal components on spacecraft. Certainly here at APL, we're having discussions with our designers and people to put metal additive parts as well onto spacecraft. Great, thank you.
Before we adjourn, we'd like to ask you to do one last task here, which is draw the winning ticket
Oh, sure.
for the book that we're giving away this evening, entitled "Fabricated: The New World of 3D Printing." And this is I didn't look at the publisher date, but I think it's pretty current, right?
Fairly recent. Yes.
Yes. So where's the tickets? Oh, there's some people who have not gotten the tickets yet.
I forget, which one of you gave me the check to draw their ticket out?
Yeah. Well, it will be probably coded with a little.
That's right. It's a little warm.
Dog ear or
Right.
something. Yeah. While we're giving the tickets out, I have two announcements. One is that Chuck Lipinski has graciously brought in a number of cybersecurity magazines that he picked up at a symposium this week, and he thought it was important enough to make you all aware of it. So help yourself as you go out on the right. And then the other is extremely important, the Master of Science in Systems Engineering at the Institute for Systems Research at the University of Maryland. Anybody that's got any questions about continuing your education, pick up one of these brochures at the back. We've got plenty of people that have not only gone through the program, but are spokesmen for that. And we think that it's something that deserves your attention. I think we're almost ready.
Nothing up my sleeve.
Yeah.
That's right. Oh, it is yours. Look.
No.
Oh.
Oh, you can go ahead and read your mic.
The last four digits are 5725. 5725.
We have a winner.
That's 5724.
Mm-hmm. He paid me more. Sorry.
There you go. Here we go. You'll want to get it presented by the author.
Well, I'm not the author, but it is a good book. I have read it. Thank you.
Come to that program where it's time to say thank you. And I think we've all learned a lot coming from different backgrounds. And on behalf of the chapter, we'd like to present you with our caffeine delivery system. And we also have a certificate that we have to yet use our 3D additive manufacturing system to produce, but it'll be forwarded on to you. So again, if we can get there we go.
Great.
Okay.
Thank you very much.
And thank you. Thank you very much. And let's have some applause for our guest.